Okay, we've established, at least in part, that for the system written here, we get solutions of this, a solution of this form, and the real part of that solution becomes this, the derivative of the real part becomes this, and the derivative of the real part is related to the imaginary part, to the real part of the original equation by these equations. In other words, the real part of this solution satisfies the equation. And we want to answer the question, why is it that we generally expect the real part to be a solution, and that we also expect the imaginary part to be the solution? Now recall that our solution was expanded and separated into real and imaginary parts, so that any such solution will have a real part and an imaginary part. So, to answer the question, why should the real and imaginary parts both be solutions? Get this down here where I can write on it a little better. If y has a real part and an imaginary part, now that just says y equals script r plus I times script I. I know that these symbols might be unusual and maybe a little frightening because we no longer emphasize cursive writing, but it has its advantages. It's prettier than printing, and it's quicker than printing. So I certainly recommend that you learn to write fluently in cursive. I also suspect, don't have any proof, but there might be some evidence that it does enhance parts of your brain that are worth enhancing to learn to do that. In any case, y is script r plus I times script I. It follows by the linearity of the derivative that y prime will be r prime plus I times script I prime. And you can go back to the solution to any of these equations and see exactly what that means. You can substitute the real and imaginary parts of the solution to the equation we've been working on and convince yourself that this must be so. From this, then, of course, it follows that the equation, our original equation, y prime equals ay, which is the equation we're trying to satisfy, if this is a solution, then the fact that this is a solution to this equation tells us that this derivative is the matrix A multiplied by this function. No surprise there, but we need to get used to the idea that we can write the function as a real and an imaginary part, and its derivative as the corresponding real and imaginary parts. Now, the linearity of matrix multiplication applies whether you're multiplying by real or complex numbers. So A times the real part, and then we have A times I times the imaginary part. I is just a constant, complex constant or an imaginary constant, still a constant. It factors out, and I'm not going to write that in two steps. I'm just going to say that's then I times A times the imaginary part. And that is, of course, equal to the real plus I times the imaginary part of the solution. But now the real part of this complex expression has to equal the real part of this complex expression. So the real part is equal to the real part. So the real part on this side is equal to, and those are both derivatives, the real part on this side is equal to A multiplied by the real part on this side. And the imaginary part equals the imaginary part. So I prime equals A I. Well, what does this say? This says that the real part solves the equation. And this says that the imaginary part solves the equation. And that's what we set out to demonstrate. This is why the real and imaginary parts have to be solutions. It comes down simply to the linearity of the derivative and the linearity of matrix multiplication. If you have those two linearity properties, you end up with this conclusion. So in general, that's why in the preceding examples, the real part of the solution of that equation was the real part of the complex solution function was a solution to the equation, and why you could be confident that if the solution was correct, you could have used the imaginary part as solution.